Hi, I'm Dr. Kelly Zimmerman, and welcome to Bug Basics, Episode 2. So, giant bugs are a great movie monster. They're also biologically completely impossible. And by the end of this video, you'll know exactly why. The answer isn't muscle or strength or evolution not getting around to it. The answer is something insects wear every single day of their lives, their exoskeleton. All right, quick reminder from last time. An insect is defined by a three-part body, 6 legs, 1 pair of antennae, and an exoskeleton, which is the skeleton worn on the outside instead of the inside. Today we're spending the full time on that alone because it explains more about insect life than almost anything else we'll cover in this series. Humans and other vertebrates keep our skeleton on the inside, wrapped in muscle and skin. Insects flip that arrangement entirely. Their hard structural material, called cuticle, sits on the outside, and everything soft, like muscles and organs, is packed in underneath it. That cuticle is made largely of a substance called chitin, a tough, layered material that's part flexible, part rigid depending on where it is on the body. Chitin is why a beetle's back feels hard like a fingernail, while the thin membrane of a wing feels almost like plastic wrap. Same basic material, different thickness and structure, doing different jobs. Think of it like this. An insect is built the way a suit of armor is built, rigid plates connected to flexible joints, covering something much softer inside. Here's the catch with wearing armor as your actual skeleton. Armor doesn't stretch. Your skin can stretch as you grow, an insect's cuticle can't. Not meaningfully anyway. Once it hardens, that exoskeleton is basically a fixed size and shape for as long as the insect wears it. So there's an obvious problem. Insects need to grow, from a tiny hatchling to a full adult. But they're wearing a suit of armor that won't grow with them. You can probably already guess the solution. At some point, the suit has to come off and a new, bigger one has to take its place. That process is called molting, and it's one of the defining, non-negotiable events of an insect's life. Molting. The technical term is ecdysis. Happens in stages, and it's honestly one of the most vulnerable moments in an insect's entire life. First, underneath the old, tight exoskeleton, the insect grows a brand new one. Soft, wrinkled, folded up like a piece of clothing packed for a trip. Once that new layer is ready, the insect splits the old exoskeleton open, usually along a weak seam on the back, and wriggles its way out. The empty cast-off shell left behind is called an exuvia. And if you've ever found a papery, insect-shaped husk clinging to a tree trunk or a window screen, that wasn't a dead bug. That was a molt. The insect that made it is very much alive, just somewhere nearby. Right after molting, the insect is in serious danger. That brand new exoskeleton is soft and pale. It hasn't hardened yet. For a window of time that can range from minutes to hours, depending on the species, the insect is essentially defenseless. Easy to injure, easy to eat, and unable to move as effectively as usual. It has to wait, often hidden, while the new cuticle hardens and darkens in a process called sclerotization. Most insects molt multiple times over their lives, sometimes 4 or 5, sometimes more than a dozen, depending on the species, with each molt allowing a jump up in size before the next fixed suit locks back into place. Now, back to that open. Why can't an insect ever get to be dog-sized? Part of the answer is structural. An exoskeleton is strong for its weight at small sizes, but that relationship breaks down as size increases. A much bigger shell would need to be disproportionately thicker and heavier just to support the animal inside it. And at some point, the math stops working in the insect's favor. There's also the molting problem itself. Every molt is a moment of extreme vulnerability, and larger animals generally take longer to regrow and harden new tissue. An insect-sized creature scaled up to dog size would need an enormous, thick new exoskeleton to grow underneath the old one, and would then be exposed, soft, and defenseless for a dangerously long stretch while it hardened. And finally, there's oxygen. We haven't covered how insects breathe yet, that's coming in episode 5, but the short version is that insects don't have lungs, and their breathing system has its own size limitations that add yet another ceiling to how large an insect body can get. Put it all together, structural limits, the vulnerability of molting, and a breathing system with its own constraints, and you get a hard ceiling on insect size. Not a lack of evolutionary ambition, just biology and physics agreeing that giant beetles stay in the movies. Here's your assignment for this episode. Go find a molt. Cicada shells are the classic beginner example. Check tree trunks and fences in late summer, and you'll likely spot one still clinging in place, perfectly insect-shaped, completely hollow. Look closely, and you can usually see the split down the back where the cicada climbed out. When you find one, you're not looking at a dead insect, you're looking at evidence. A discarded suit of armor from an insect that's out there right now, wearing a bigger one. So to recap, insects wear their skeleton on the outside, made from a material called chitin. Because an exoskeleton can't stretch, they have to periodically molt and shed the old shell for a new larger one. That process leaves them soft and vulnerable until the new cuticle hardens. And that whole system, combined with how insects breathe, is exactly why you'll never meet a dog-sized beetle outside of a movie screen. Next episode, we're zooming in on the front of the insect body, the head. We'll talk about compound eyes, why some insects can basically see in almost every direction at once, and how insect mouth parts are less like a single mouth and more like a specialized toolkit, depending on what the insect eats. I'll see you there. Thanks for watching.